Good morning, everyone. Hope you're doing all right. Enjoying this lovely, lovely weather right now. Making me jonesing for bike rides and runs outside and hikes and camping. Been really nice. So we are going to continue on with chapter 8. You will have your final test, or not your final test, sorry, your third test this come on, why is this not opening? Okay. You'll have your third test this Sunday, Monday. We do meet on Monday, so I'll make sure to give you another reminder then. And it'll cover chapter 6, 7, and 8. So let me share screen and we can revisit. Just a couple definitions before we do an example problem, because I want to do another one of those limiting reactant example problems because they're tricky and they are time consuming. So we talked about this idea of stoichiometry and its relationship to baking, and how if we have a balanced chemical equation or a balanced recipe, right, we can come up with the amount of reactants we need, the amount of product we will get, all sorts of different things by using the coefficients. We had talked about some definitions. So the limiting reactant, remember, is the reactant that is completely consumed in the reaction. It's whatever's holding the reaction back. So it is going to limit how much of the product you can produce, right? The excess reactant would be whatever you have an additional amount of. The theoretical yield is the amount of product that you would create based off of the limiting reactant. So it's the lower amount of the product that you could potentially create. The actual yield is the amount that you actually produced. Again, actual yield is going to be given to you guys, or you would have to find it experimentally. And then the percent yield is A over T times 100. So we are going to calculate some of these things: limiting reactant, theoretical and actual. Where did you go, you pesky downloads? I finally updated my computer, and now everything's like in a different place, and I don't like it. When I download things, it doesn't do it the way I would like it. Okay. That's more, I want that to be more practice for you guys. Let's try a different one. All right, well, I'm just going to make one up then, because these are good for you. The worksheets are good for you to practice, but they don't give you like a complete limiting reactant problem, so I can just come up with something. So let's say we're going to look at the oxidation of iron. So the oxidation of iron, we take iron, we combine it with oxygen, and we're going to produce iron 2 oxide, or iron 3 oxide, so Fe2O3. Okay, this is the skeletal formula. I'm going to just go ahead and balance it for you all. So I'd want to put a 2 here, I'd put a 3 here, and I'd put a 4 here. So let's say we have 9.62 grams of iron and 18.4 grams of O2. What is the limiting reactant? And what is the theoretical yield? So you have a balanced equation. You have two amounts, right? This first amount is talking about iron. The second amount is talking about oxygen. And I want to know which one of these is holding the reaction back and what your theoretical yield is. So in theory, how much of this stuff over here can you produce? There's only one product, so you're just going to work towards that product. So I'm going to give you all about 5 minutes to do this first step. All right, it's going to follow that same structure of grams of A into moles of A, into moles of B, into grams of B. That's sort of our golden flow chart for stoichiometry. If you have any questions too while you're working on it, just go ahead and turn your mute off and you can throw it out there.
I'm a little stuck here. Can you hear me?
Yeah, I can hear you. Sorry, my
Okay.
mouse pad wasn't working. What's up, Elizabeth?
Okay, so I'm like, to go to like figure out the oxygen, moles of oxygen. And the left side of the equation, we've got 3 moles of O2. So then to do the dimensional analysis of that, I'm just like, I can't remember how I'm supposed to do that. I've got 3 moles of O2.
So did you get from, we can sort of start chipping away a little bit together, and then maybe I'll take a break so you can kind of finish it up. But let's start with the O2, okay? So we have 18.4 grams of O2. And the first step is to convert it into moles, right? So was that not too bad? You just use the molar mass?
Well, actually, I was a little confused about that too, because am I supposed to say 32?
Yeah, so when you see it written as a diatomic, take into account that it has 2. Do you see how here this is 1 iron?
Yeah.
This is 2 oxygen. So we do want to take that into account. So 1 mole of the O2 is actually going to be 32 grams. So that's step 1. That gets us from grams of A into moles of A. And again, A just being an arbitrary thing for like our reactant. So now we want to go from moles of A to moles of B. This is that magic step that we get to use the coefficients. Okay, so if we're looking at the relationship between oxygen and the product, what I see in my balanced equation is that 3 moles of O2 will yield 2 moles of the product, of the Fe2O3. Because these are mole rate relationships. So if this has a 3 and this has a 2, it's a 3-to-2 ratio. You like that, Elizabeth?
Yeah, I'm confusing myself with the coefficients and the subscripts, I think.
Okay, yeah. So think of the subscript as like the definition of what that compound is. All right. If it's got 2, you got to make sure you take into account 2. Just like over here, if you have 3 oxygens, you got to add up 3 oxygens. So that is what the identity is of the compound. The coefficient is the ratio between those 2 compounds. Okay. So next step here, once we've gotten into moles, is to use just the ratio of the coefficients. So if O2 is on top, let's put that 3 moles of O2 on the bottom. And we'll put the 2 moles of the Fe2O3 up top. Then that last step is to go from moles of whatever B is into grams of it. So 1 mole of Fe2O3. Does anyone have the mass on that? I'm too lazy to calculate it.
159.69, I think.
That sounds about right. 159.69 grams of Fe2O3. So if we, go through the process of calculating this out, 18.4 times 2 times 159.69, everything on top gets multiplied. Then we divide by 32, and then we're also going to divide by that 3. So I end up with, if we have 18.4 grams of O2, we should be able to yield 61.2 grams of the Fe2O3. Any questions on that, Elizabeth? Does that feel a little bit clearer?
No, I understand that now.
Okay.
I'm just confusing myself with trying to figure out, am I converting 6 moles of oxygen to 6 on the other side? But no.
So, and that's super common. I see that happen. So on the outer steps here and here, that's where you want to use the molar mass that takes into account subscripts. The inner step here, that's where the coefficient happens. That's the stuff sitting in front. So As far as this problem's concerned, we are sort of at the halfway point, right? We've calculated for one, we've got to do it for the other one. So 9.6, 2 grams of iron. First thing is to convert iron into its mole amount. So 1 mole of iron always has a mass of, what is it, like 56? I don't even remember. 55. 55.8. Oh, come on. 55.85. Close enough grams of iron. We don't double it up because iron isn't a diatomic, right? So there's no 2 subscript or anything like that. So we don't have to take that into account. Now we get to use the coefficient. So it's like subscript, then coefficient, then subscript. So coefficients, well, we have a 4:2 ratio. 4 moles of Fe will yield 2 moles of the product, Fe2O3. The next step is to get it into grams of the product. And because you've already calculated it, it's the same number for both, right? So one, because we're working towards the same product. So one mole, not one mom, 1 mole of Fe2O3 is 159.69 grams of that product. So grams of iron cancel, moles of iron cancel, moles of the product cancel, and we should just be left with grams of the product. So throwing this in the calculator real quick, we've got 9.62. We multiply it by 2. We multiply it by 159.69. And then I'm going to divide it by 55.8 and divide it by 4. And I get 13.8. Sorry, my trackpad is giving me a real hard time today. 13.8 grams of the Fe2O3. So again, it's not always the case that the thing with the lower amount equates to the limiting reactant because these have different masses. This just happened to work out that way. But as far as what's the limiting reactant, iron is our limiting reactant. The word limiting reactant is asking you which reactant is limiting. It's not a number value, okay? It's a compound value. The theoretical yield is going to be whatever gets produced from that limiting reactant. So this is our theoretical yield. If we were going to run this equation and we had these exact amounts, in theory, if I was perfect at running it, I would get this amount. The last thing I want to go over is actual yield and percent yield. So let's put like a B, part B on this. Say that this was A. We'll say this is B. So the actual yield is 7.55 grams of Fe2O3. Calculate the percent yield. All right, I'm just going to give you about 2 minutes for that one. That one's not too tough, okay? Okay, so this is a real quick one. Percent yield, sometimes it's written like this with the percent sign instead of writing out percent, but percent yield is equal to actual over T, or actual over theoretical, times 100. Remember I told you all actual is going to be given to you. Well, there it is in the problem. Theoretical is something that may be given to you, or you may have calculated it from like a previous step in the problem. So we've got the theoretical right here. So I'm going to take my actual, which is 7.55 grams. I'm going to throw it over that theoretical, which is the 13.8 grams. And I'm going to multiply that bad boy by 100 so that I'm in a percentage. This is already looking to me like a pretty bad percent yield. Yeah, so we're getting a percent yield on this reaction of 54.7%. Right, so just over half of the reaction is actually occurring. The rest is sort of being stalled or wasted or whatever is going on in this reaction. Okay, questions on this? I will have one more thing in this chapter to talk about, but it shouldn't take me more than and probably get it in about 15 minutes. So we can do another one of these if you guys want to. You got to tell me if you want me to do another one. I don't particularly want to do another one because they are time consuming, but if you want another one, I will totally do it for you. You just got to tell me if you're not getting the concept. Write it in the chat or turn your mute off. I will definitely go through another one. No one? No takers? Elizabeth's like, no way. I got it. Okay, so you will get more practice with the homework on this. If you do decide later on that you're like, I need some more work with this, go into, let me pull it up here. Go into these worksheets here, and there's a stoichiometry practice down in here. And you could even probably run through this limiting reactant one we did the other day. I doubt you've got it memorized. So you could definitely pull this one back up. If you go online too, you can always just do a search for limiting reactant practice problems. But this is a great way you can rework your through this limiting reactant problem. Okay. Again, what was that?
Do the worksheets have the answers provided too?
The first one doesn't, but we went through it the other day, so you can always review the video. The other ones do have the answers. That's why I wanted to specifically go through that one. But the other ones, yeah, they do have the answers buried in there somewhere. Oh, maybe not this one. If you do end up working through that and you just want me to check it, just email it to me and I can check it for you. The other one, this one does, no, not this one. Where are you? This guy here does. Okay, it has all the answers down on the bottom, and there's 2 sets of pages there for you to practice stuff. Okay. So the last thing I want to talk about with this is energy in a chemical reaction. So enthalpy is a fancy way of giving a quantitative value or giving like a numerical value to the amount of heat that is either emitted or absorbed in a reaction. So sometimes you'll see equations and it'll say like combustion of methane produces heat, and it's just like a general word, heat. It doesn't have a number to it. Well, enthalpy gives it a value. All right, how do you calculate enthalpy? That's something that you would calculate experimentally. But the amount of thermal energy that's emitted or absorbed is actually going to be directly related to the chemical equation. So we define the enthalpy of reaction, and sometimes you'll see it as this simple delta H of reaction, as the amount of thermal energy or heat that flows when the reaction is at constant pressure. You're just going to assume everything we're dealing with is at constant pressure, okay? So when we combust methane, we don't get quite as much thermal energy as we do when we combust octane. That's why we run our cars, our big hunky cars, we run them on octane. There's more carbon in there than we would, wouldn't want to run them on methane or propane that has fewer carbons. So it is important to note what the sign is of the delta H of the reaction. Energy flowing out of the system, so if it's an exothermic reaction, will have a negative sign because it's losing energy, right? Energy flowing into the system or an endothermic reaction will carry a positive sign. So another way we can look at this in an exothermic reaction, if you're losing energy, that means your reactants have a lot of energy. You lose energy and your products will have a lower amount of energy, right? This is energy on the x-axis or the y-axis here, higher energy, lower energy. So my reactants have a lot of energy. We run through the reaction and my products now have a lower energy. In an endothermic reaction, the opposite is actually true. We've got our energy line here. Our reactants have a relatively low amount of energy and they eat up or they absorb energy from the surroundings to give products with a higher energy. That's why your delta H of reaction in an endothermic is positive because what you're ending up with is more energetic. In an exothermic reaction, your sign is negative because you're ending up with less energy. So let's see how this looks in the combustion of methane. Now, again, I don't expect you to know that this is methane, but I would want you to know that this is a combustion reaction. There's a hydrocarbon, carbon and hydrogen. What is it doing? It's combining with oxygen. It produces CO2 and H2O. That's always what's going on in a combustion reaction. Now, do you see how underneath this reaction, there is a numerical value here? This is your enthalpy or your delta H of reaction. What this says is that every time you run through this equation in a stoichiometric way, so 1 mole of this, 2 moles of this to produce 1 mole of this and 2 moles of this, this is how much energy is released. You get 802.3 kilojoules. Where is this number coming from? Do I expect you to calculate this number? No, this will always be given to you, okay? So don't get freaked out about, I have to have these memorized or I have to calculate. You don't need to calculate these. It will be like clipped in underneath the balanced equation. Now, just like these are stoichiometrically related to each other or molarly related to each other, like 1 mole of this equals 2 moles of this, right? Or 2 moles of this produce 1 mole of this, or 1 mole of this produces 2 moles of this. The same thing is true for the relationship between the amount and then the amount of energy. So looking at this equation, 1 mole of methane, if I was to combust 1 mole of methane, it would produce negative 802.3 kilojoules. Okay, that's the relationship. What about its relationship to oxygen? Well, there's a 2 in front of it. So 2 moles of the oxygen will produce this much energy. Okay, let's just beat a dead horse. What about if we produce 1 mole of CO2? There's a 1 in front. What is the 1 mole of CO2 going to give us energy-wise? Same relationship, okay? Negative 802.3 kilojoules. And then to finish it off, if we have 2 moles of water produced, and that is unique to this equation, it has to be talking about this equation, we will produce this much energy. So this is kind of cool because now you can go from an amount into an energy value, right? This is a conversion factor that takes us from a gram or rather a mole value into an energy or joule value. Let's look at an endothermic reaction. So here is a reaction where it is absorbing energy. How do I know it's endothermic? Because the delta H of reaction has a positive sign. When I synthesize NO from nitrogen and oxygen, this is how much energy it eats up or absorbs. So let's talk about some of the relationships. Well, what do we have here? There's an inferred 1, an inferred 1, a 2, and then this information here. So 1 mole of N2 needs how much energy to run this reaction? This much, plus 100, positive 182.6 kilojoules. What about the oxygen relationship? 1 mole of O2 is going to, if we run this reaction and we have 1 mole of O2, it's going to be this much energy, positive 182.6 kilojoules. And then again, just to the last nail in the coffin here, 2 moles of NO. How much energy? This much energy. So you've got like another value built in. So I could give you an amount of any one of these, and you could tell me how much energy it needs or how much energy it produces, depending on the equation. Let's do that. All right. I don't really want to do this one just yet. So let's go back to this one. Sorry, this pen is driving me crazy. Okay, so how much energy is produced, or I'm sorry, it's not produced, is needed to make 18.4 moles of NO. How much energy is needed to make 18.4 moles of NO? And this is our equation, and here's our delta H. So with this, I am given, sorry, I'm going to kind of write this down here. I'm given that I have 18.4 moles of NO. And I want to find energy. Energy, if it doesn't explicitly tell you what the unit is, you can just go with whatever this unit is. So we'll just go with energy in kilojoules. So what's my relationship between NO and kilojoules? Well, 2 moles of this makes this much energy, right? Or needs this much energy. So I start with my given information and I just do a quick conversion. For every 2 moles of the NO, I am going to need a positive 182.6 kilojoules. Do you notice what happens to the moles? They disappear. And you'll be left with just these units of kilojoules. So we find our 18.4, multiply it by 182.6, and then divide it by 2. And we get a decent sized number. Come on. Come on, pen. Okay. So we get, we had 3 sig figs, so 1680 kilojoules. Now we're in units of energy. So we went from an amount to energy. How often are things given to you in moles like this? Not very often. What are they usually given to you in? Grams. So if you were, instead of given moles of NO, you were given like a gram of NO, what's the first thing you need to do? You need to go from grams into moles, and then you can go from moles into the energy. So let's try that out. We'll reuse the methane reaction. And I'm going to do it on a separate sheet because this is too tight. So here's our combustion of methane. I'm going to copy it over here. You can follow me along as we write it out. So the methane reaction is CH4 plus O2 produces CO2 and H2O. Always balance your carbons first. Those are balanced. Then balance your hydrogen. There's 4 there. There's 2 there. I'm going to put a 2. And we are, we've got 2 oxygens and 2 oxygens, so I need to put a 2 here. Okay. The delta H of reaction for this guy is negative 800 and something something. Thought I had it memorized. 802.3. 802.3 kilojoules. It's negative because it's exothermic. Exothermic means it's losing energy. Okay. So let's say I want to know how much energy is produced when combusting um, 154 grams of CH4. I'll give you all about 3 minutes for that one. So how much energy is produced? And when I say energy, you can give me the value in kilojoules. That's fine. So how much energy is produced when combusting 154, hint, hint, wink, wink, grams of CH4? Okay, so the relationship between a balanced equation that we've got up here and the delta H of reaction is going to relate moles to energy, and energy specifically for this one is in kilojoules, right? So it's going to relate moles to kilojoules. We're not given moles. What are we given? We're given grams, but that's okay. Start to really think about grams and mole as being really interchangeable as long as you know the molar mass of the compound, right? So I'm going to go from grams of the CH4 into moles. What is going on here? Let's try that again. Grams of CH4 into moles of CH4. And then from there, we can go into energy or kilojoules. This first step is just using the molar mass of CH4. The second step is using the relationship between methane, which is this guy over here, and the delta H of reaction. How do these things relate to each other? Well, 1 mole of methane, and the reason I picked 1 was because the coefficient was 1. If we had been talking about oxygen, I would need to use the coefficient of 2. 1 mole of methane will always produce or yield 802.3 kilojoules as long as the equation is run efficiently. This is the molar mass of methane, carbon, what is that? It's roughly 16 grams, close enough. All right, so let's convert. So we've got 154 grams of CH4. Let's get it into moles. 1 mole of CH4 is roughly 16 grams of CH4. And then from there, I know that if I have 1 mole of methane, this is how much energy I'm going to release. I'm going to put the sign in there just to remind me that this is an exothermic, or the energy is exiting or is being produced. What I find is we get a pretty big number. I got 77,022, 7,722. It's 3 sig figs. I was real crappy with my precision on that one, but 3 sig figs should probably do it. So 7,720. And the units on this are kilojoules. That is, and it's a negative value, letting you know that that is the energy that's being produced. Okay? So you can go from an amount into an energy value as long as that value is given to you. Obviously, if this just was not present, you would not be able to do something like this. Okay, so that will be given to you. Any questions on that? On how we can go from an amount to an energy? Looking at the slides here, they do have an example in here, which is really similar to the one we worked on. It says, here's a balanced equation for the combustion of propane. So propane has 3 carbons instead of 1 carbon like methane, but it's still the same idea. Propane is combining with oxygen to produce carbon dioxide and water. Do you see how you get a lot more bang for your buck? Look how much energy gets produced here. Whereas methane only produced like about 800 kilojoules, this produces over 2,000 kilojoules. Okay. If it said, hey, we've got a barbecue tank, and the barbecue tank contains 11.8 times 10 to the 3 grams of propane. Don't get freaked out by the 10 to the 3. That's just saying, you know, move the decimal over 1, 2, 3, or it'd be 800. Okay, it'd be 11,800 grams. So we have quite a bit of propane. It says calculate the heat in kilojoules associated with the complete combustion of the tank. So we know a gram amount. We want to find a kilojoule amount. Well, our middle step is going to be the mole, right? So we need to go from, I think it's on the next slide actually, so I'm going to write it out. we want to go from grams of the propane into moles of the propane. And then from moles of the propane, we can hop into our kilojoules. How do we get from grams to moles? Molar mass. Always like interchangeable with molar mass. How do we get from moles of propane into kilojoules? That is using the coefficient and the energy. So in our original equation here, we see that for every 1 mole of this is how much energy will get produced. So we end up with this sort of setup for our dimensional analysis. Units cancel and it says, hey, you produce negative 5.47 times 10 to the 5th kilojoules. It says often in the homework, the absolute value of Q, absolute value just means that you remove the sign, is used if the wording is right. So if this problem said, hey, how much energy is produced? The word produced is sort of encompassing the negative, right? If I say produced, I don't have to say negative 5.47. I would just say 5.47 times 10 to the 5th energy is produced. Kilojoules of energy is produced. Okay. So you definitely have a problem like that on the test. So you want to be able to do that. I would obviously give you the balanced equation and I would give you the energy. So as long as you kind of remember this flow chart, you should be good with that. And that's it for this chapter. So that next test that's coming up here will be chapter 6, 7, and 8. I do think it is the most cumbersome of all the tests just because of all the math and the different ways of mathing, right? So I would start, if you haven't already, I would start your studying now, go back, review chapter 6, what was happening in chapter 6, and then get to chapter 7 and 8 without having to cram right before. That is all I have for y'all today, though. So if you do have any questions just about problems that you've been working on, let me know. Or if you have any personal questions, then we can wait and talk one-on-one, right? Otherwise, enjoy your day, get outside. It's so nice out. And I will see you next Monday. Okay, bye guys.